Good afternoon. Sorry for the delay. I was in another meeting and I had to delay this particular talk. But today we're going to have an interesting talk about fine and coarse grain simulations. And then we'll have a demo of the coarse grain simulation, because fine grain simulation is basically MD molecular dynamics simulation, okay, and using GROMACS. So what are the limitations, what we mean by fine grain, what we mean by coarse grain, we'll see in this. Apologies in advance, my voice is a bit hoarse because of some reason, I don't know. So I will be speaking a little bit slower and a little bit able to, like, at a low volume. So in case you're not able to hear me, do let me know. I'll try to increase my volume and speak louder. Okay. So what are fine grain simulation? Fine grain simulation are nothing but molecular dynamic simulation, where we want to see what the atomistic movements are. Okay. So in the application for these is dealing with biomicromolecules like proteins, DNA, lipids, carbohydrates. But molecular dynamic simulation can be applied to other methods also, like in civil engineering, in mechanical engineering, in chemistry, and so on. So the in a very simplistic manner, we are uh, demonstrating, or we are checking uh, the Newton's second law of motion using a molecular dynamics simulation, specifically classical mechanics. Okay, so there is quantum mechanics, there is statistical mechanics, and then there is classical mechanics. Classical mechanics compared to statistical and quantum assumes a lot of things, but it is the most easiest way to study for protein structures. So what we do is we calculate potential energy and with respect to the atom positions, because we know every atom where it is. And then we give a acceleration in terms of uh, temperature. So when we heat up the system, the molecules start vibrating. So when I say heat up the system, not boiling temperature, basically in terms of Kelvin. 0 Kelvin, everything is frozen. 300 Kelvin, which is room temperature, there is a lot of movement seen in molecules. So when there is a movement seen, when we have the velocity with respect to time, we get acceleration. So we have mass, we have acceleration. The second law of Newton says F equals ma. So we are trying to see what is F. So we try to deduce, by giving an acceleration in terms of temperature, what is happening to that system. And we obtain those forces. Now, since the system changed after a particular period of time, then we calculate the potential energy again. We see the differences in the terms of potential energy, and then we give another set of velocities. And then we do this many times, typically more than 1 million times. This is the molecular dynamics simulation. Very simplistic way of explaining, but I have assumed or have moved over a lot of intermediate steps. So what is the advantage of this? It's very easy to use. You get dynamics data of the atoms and molecule. It's almost like creating a movie of a protein. So you can have setups like protein in vacuum, protein in water, protein in benzene, or a different solvent, and you can see how the protein behaves. Many structural features can be extracted in an MD simulation. And the more the parameters and more the constraints are there, you can get as realistic simulation as possible. But understand that this is a simulation. That means there is some amount of error and it is a prediction. So there is some limitation. It is less accurate when uh, we have experimental data not available for the molecule. Also, for a very large scale or a very long-term process, like let us say a protein behavior in terms of minutes or hours or days, that cannot be done. We can see at the level of nanoseconds, microseconds, or at the maximum millisecond. Okay, not beyond that. 1 second, just give me a minute. You see, guys, are repairing the something on the block ventilation. Okay, I hope you are able to hear me now. Okay, so it also cannot be used for breaking or making covalent bonds because that doesn't exist. Okay, in our current setup, whatever material, whatever tool, whatever force field we use, we can continue the existence of covalent bonds, but we cannot see breaking or making of covalent bonds. For example, there is a protein which is bound to a drug. We want to understand whether a mutation in the protein can lead to a drug resistance. You can use a simulation. So you start with the experimental structure, most probably by X-ray crystallography, and then you put water in it. So basically you create a box and then you put water molecule in it along with the protein and the drug. And then you solve the second law of Newton. Whatever we do is all this is what I explained earlier. Then what you see is if let us say there is a mutation and you have the setup with a mutant and the inhibitor, and you have a setup without the mutant and the inhibitor, meaning without the mutation and the inhibitor, then what happens? You can see differences between them. And those differences can be in terms of bond, can be in terms of conformation, can be in terms of energy. There can be many different things that you can analyze. So we take very short time steps, 1 to 4 femtoseconds. The reason is this is the time taken for a hydrogen bond to create or break. Now, hydrogen bonds are not covalent bonds. Covalent bonds are C double bond C, C triple bond C, C, NO, and also it. Okay, so they are different type of time scale that is involved in bond formation and bond simulations. Okay. Now, what is the output we get? The output we get is what we call as a trajectory. That is the term that is used. Okay. Trajectory is a, like a movie. Like I said, is a movie. But that movie is not a continuous movie. It is made up of snapshots. When you combine more snapshots, you remember the flip book, you can flip it. And if you take many photographs, you stack one above the other, and then you flip the book, you get an animation. That's what you call as a trajectory. So there are a lot of programs that are available to view the trajectory. You can watch the simulation just like a movie. You can zoom in, zoom out, you can skip some frames, or you can see all the frames. So this simplicity and also with computational power, lot of analysis, lot of people, lot of systems are available where they can observe what is in a system. The hydrogen bonds, distance between the atoms, modification of secondary structures, change of volume in the active site, which is where the drug is going to bind, and so on. So, such observables yield a biological insight. There are many different packages. I'm not going to go into detail. There is Amber, Charm, Chromax, NAMD, and these are the websites. You can look at it. Some are academically free, some are commercial, some are completely free for anyone to use. The trajectory viewers, you have PyMol, you have Chimera, you have Vient. Okay, so what Nisha, my PhD student, is going to show you is using Vient. Yes, Nisha, or will you show Chimera or Vient or PyMol? Which one you are going to show? Because I saw VMD.
I'll be using VMDs to demonstrate it.
Okay, you have to be a bit more louder when you speak. Okay. Okay, so she is going to show the demo in VMD. Okay. From a biological perspective, what are the uses of the molecular dynamics simulation? You can use transporter proteins to find out what is the process of the transport happening from extracellular part of the cell to the intracellular and vice versa. How is the molecule being transferred? Which residue is playing a major role? What mutation, if it happens, is not involved in the contact of the substrate or it's involved in the substrate contact. Computer-aided drug design MD simulation can show you what happens to the molecule in terms of energy, in terms of electrostatic and hydrophobic forces. It also can be used to study post-translational modifications by comparing modified and non-modified proteins. So these are just a glimpse of what can be done, what type of biological question can be asked. But this is not just the questions. There are many different questions. There are more limitations in MD simulations. You can only do it for soluble proteins that are already known to bind to some inhibitor. If they are not known, then it's a bit tricky because you don't know what is binding, what is not binding. Then when there are multivalent metal ions, there are more variables in the system, meaning more cofactors, membrane bound, and some other specific protocols are needed, then it becomes very complex. Also, as of now, even with a supercomputer, they can do 5 or 2 millisecond or 1 second simulation. That 1 second simulation can be done for a small system, 50 amino acid, 100 amino acid. For more than one protein or more than 5 proteins, you can do 1 millisecond simulation. You can't do more than that. The time scale is very small. Now you might ask, 1 millisecond is just a snapping of a finger. How much time does it take? Well, the paradox is that in human time, 1 millisecond is a snap of a finger. But in computation time, 1 millisecond can take 3-4 months, depending on the system. Sometimes it may be 1 year. So 1 human year. Okay, so it takes a lot amount of time. Then conformational changes with protein domain will need more elaborate methods or some specialized hardware like GPU, graphical processing units. Okay, so that may hinder the progress. Now, what I talked about classical mechanics or the MD simulation, which is we call as canonical MD, they involve potentials that are based on classical mechanics, which do not allow breaking or formation of covalent bonds. That is allowed in statistical mechanics and quantum mechanics. Those simulations cannot be done for macromolecule. You can do it for small chemical structures like small acid-base reaction or exchange of nucleophilic attack, electron transfer. That's all. Not more than 100 atoms. So you have hybrid methods that overcome all these limitations. Quantum mechanical, molecular mechanics, simulation, hybrid, or AI-based MD, or simplified coarse grain. In quantum chemistry, what is the strength? Now I'm going to the other part. You can say, okay, I want to do quantum chemical analysis simulations. Yes, you can do it. What is the advantage? You can look at electron level information of breaking and making bonds and the excited states of molecule. Okay, that can be done. But the limitation, it's very, very slow because it's not slow because of the molecule. It's because of the computational. You can do only short time scales and you can do only smaller systems, not more than 100 atoms. That's it. Example, you want to understand how a certain carcinogen interacts with a nucleic acid base. For example, ethylene bromide. Ethylene bromide will intercalate with the DNA. So it's a known carcinogen and it will go in between the DNA and it will intercalate. The next round of DNA replication, there will be a base lost because ethylene bromide cannot make a bond. So the base will be lost. So that's a mutation. You can use it to study, as I said, the third time, for finding bond breaking and formation. And you can also study many quantum level principles which are difficult to grasp by non-experts in a quantum mechanics simulation. To make things more complicated, quantum mechanics, they use a lot of technical terms. And then you need to have a good understanding, at least a master's level understanding, to understand what is LUMO, FUMO, and other types of terms. Okay, orbitals. You know some of those hybridization from basic chemistry, your 11th and 12th, if you had chemistry. But they are a little bit jargony in nature. Due to the high computational cost, with full protein, you cannot do minimum calculations or QM calculations. So what we do, we take the protein, we ignore everything other than the atoms that are involved in the catalytic site or the function of the protein. Rest is ignored. Okay. So some of the techniques that can be used is density function theory or DFT. So yeah, anyone has any doubts? Tarak Singh, do you have any doubt? You muted your mic. You can ask questions.
No, sir.
Okay, sounds good. You can keep your mic muted. Okay, sounds good. Okay, so DFT is a technique that is very commonly used. So this was developed by Hornberg, Kohn, and Sham in 1960s, which has transformed quantum mechanics, but it's very common to apply in biological context. For example, as I said, carcinogens interacting with DNA for chemotherapy, okay, or to study mechanism of histone deacetylation and other applications. Then there is the hybrid method, quantum mechanics, molecular mechanics, QMMM. What is the strength? You can use it to study large proteins because it overcomes the limitation of the QM method. But limitation is it's also equally slow. And but the thing is, it is a much better way to study long range effects of the protein to this particular set of atoms that we are studying. So we study QM for this part, and rest we use molecular mechanics for this part. You can also use Monte Carlo simulation for remaining part of the protein, QM for the active site. You can do like this. For example, enzymatic reaction. So you use QMMM. So part of the system will be quantum mechanically treated. Rest of the protein will be done the classical mechanical way. So you can study macromolecule involving the reaction that is taking part in bond making, bond breaking. This is fast because you're doing QM only for the small area and there are a lot of approximations used. So it is easy to do. So from a practical point of view, you can employ QMMM that requires expertise in both methods, QM and classical mechanics or molecular mechanics. They are very frequently used in biology and in drug design. Like for example, drug that covalently bind to DNA. Now comes the coarse grain approach. The coarse grain approach, we use normal mode. Normal mode is nothing but, right now you can look at my video and I'll tell you an analogy. Take some. There are two people standing at a distance. They have a rope connected between them and this guy is slowly moving the rope up and down. What happens? The wave propagates and reaches this person. Now, depending on the amplitude of the wave, you have either slow frequency waves, or if that person is moving very fast, then you have high frequency waves. So, a combination of all of that is a normal mode analysis. It's a very simple method, very fast, very easy, a very quick way to get the glimpse of the dynamics without running a full simulation. Limitation, it is not with time scale. The slower amplitude movements, the fast amplitude movements are not bound by temperature. Okay, sorry, by time scale. And also by temperature, pH, other physical chemical properties. So then you can apply it on many things. For example, you are studying a large protein, there are many domains. You want to learn how the domains move with respect to one another. Okay, it's very difficult to do in MD, but very easy to do in normal mode analysis. You can take this. Now, in equilibrium state, the protein moves, opens up, closes, or it goes through this motion. That is intrinsically present in the protein. So these motions are considered harmonic, meaning they have a Gaussian distribution. They have a normal distribution. If they can extend up to this point, they'll compress to a certain point. That's so you can connect the spring and you can use Hooke's law to study the motions, the harmonic motion, similar to a wheel on a spring. So low frequency mode represent collective motions that involve large parts of the system, like the two domain moving, and fast modes are local fluctuations. So you can study both together. So the global motions are relevant from the physiological standpoint, but it requires additional analysis to confirm whether that is indeed the physiological motions that are observed in reality. So you have molecular dynamics, you take different snapshots. This is a snapshot, this is a snapshot, this is a snapshot. So this is with respect to time. And then you have this protein which it goes under some combination of motions, and with respect to Brownian dynamics, which is random motions, you can do molecular dynamics to see how this peptide is binding to the protein. Okay, you can see, oh, the peptide is binding here, peptide is binding here, or something. With a normal mode, you can get the slow modes or the fast modes. So this is the overall of both the fine grain and coarse grain. Okay, what do you need to keep in mind? Even though in normal mode we assume the motions are harmonic, proteins are not harmonic in nature. Some part of the protein dynamics are harmonic, some are not. The system needs a proper perturbation before performing NME, which is very difficult for certain proteins, where the proteins has many thousands of degrees of freedom. Now, you don't look at the atom potentials or you don't look at the level of atoms in a normal mode analysis. There's a coarse-grained approach. So a simplified model. Downside of simplified model is that some information is lost. So you have to keep this in mind. The completion cost is not prohibitive. It's very fast, but you lose some information. Like for example, if you want to compare between a wild type and a mutant kinases, the level of resolution of the information may not be critical in kinases when you do a normal mode analysis. At the same, when you do an MD, you can see it. Okay, and so on for many proteins. So what are the different normal mode tools that you can use? Add ENM, ANM, LNEMO, OGNM, okay, Nomad, WebNM. All these are web servers. Some are tools that you can download and you can do the normal mode analysis. One such normal mode analysis is elastic network models. So elastic network models, I'll just show you. It's a coarse grained approach where we look at amino acid level. We don't look at the atom level. Just like normal mode, we decompose the dynamics in slowest and fastest motions. Two such ENMs exist. One is Gaussian network model, which gives the magnitude, and as an isotopic network model, which gives us the direction. Both are required to see the coarse grained dynamics. I'll quickly go to the example and show you. Okay. Let us say you have a protein which are you only take the alpha carbons and then you connect if any two alpha carbons are within a range of, let us say, 7 angstroms. These two alpha carbons may not be sequentially present in the protein. They may be coming closer in space. So when they are doing like that, you connect them with a spring. So you take the protein, you convert it into springs. All these gray lines are springs. The red one is the backbone. So what you do is you take the elastic network models and you start seeing the slowest mode. In this particular case, the slowest mode here, this is the top view, this is the side view. This is the protein is going in a shear-like motion. It is going zigzag, zigzag like this. If you draw a line here, that is the hinge using which it is doing the zigzag motion. Now, when I want to compare two proteins, one is a thermophile, the other one is a mesophile, I see similar motions, even though both these proteins do different functions at different temperatures or similar functions in different temperatures. It can be anything. Similarly, in the second slowest mode, you see the motion of opening and closing. But again, the hinge is here. So these two motions together probably are responsible for the biological function. It undergoes a open close and then a shear motion, or a shear motion, then an open close. We don't know. Until unless we study the dynamics in a much experimental way, we can find it out. Okay, so the great simplification is that you reduce the number of degrees of freedom which you have in molecular dynamics simulation. So by building an elastic network model, you carry out normal mode analysis and you can find out which parts of the region in a protein are rigid and flexible. Like for example, here, the ones colored red are highly flexible. The one in blue are not so flexible. The one in green is intermediate. Same with the second slowest mode. Okay, ones that are red are highly flexible. These residues or the spheres that you see are the active site residues, they are involved. So most of the motions are happening on the active site. You see here on the side view, that is a biological insight you get from a normal mode analysis. Okay. So what we found was that loops are more mobile in the slowest modes. The nucleophile and acid-base donor show positively correlated motions in the thermophile, but not in the mesophile. And the kinetically odd residues are located on the substrate binding site. which is crucial for the function. And we also saw through GNM that the thermophile contains larger dynamic domains. So we also did this with another set of proteins called lytic polysaccharide monooxygenase. At the time there are 4 families. They all look similar. And when we look at the first 3 slow modes, everything is on the substrate binding side. The 3 red spheres are the active site residues. This is the side view, this is the top view, this is the AA9 family. And we see that these loop regions are highly mobile. The arrow indicates the direction or the magnitude of the movement of that loop. Similarly for another family, AA10, similarly for AA11, similarly for others. So what we saw was that the loop regions, again, even in this protein, the active sites are very mobile. These motion are required for the substrate binding, which is cellulose and chitin in LPM. And the residues that are predicted to be co-evolved are present on the non-substrate binding side of the LPM, which we saw where there is not much of a movement happening. Okay, so in general, this you take a lysozyme structure, you can see the lysozyme, you see the arrows, this side of the protein is going in one direction from right to left, this is going from left to right. So it is an open and close movement. You can observe this biological insight using a coarse grain approach. And you can also see conformational change happening between the same protein or a different protein in this particular case using El Nemo. So you see different the combinations, but the molecule that's binding, there you see very minimal change happening. This is opposite to what we saw. So depends on what the protein is, depends on what information is there in the protein. Your coarse grain results will be different. Your coarse grain results will give a different biological insight. Your molecular dynamics simulation will give a different biological insight. Okay, so this is a ANM or anisotropic network model of a copper transporter. These helices are present on the outside of the protein. This is the place where the copper is passing through the extracellular to intracellular. You see that it is opening and closing, and allows the copper to go through the pore of the protein. But the atoms that bind to the copper, you don't see many movement. So that means it is involved in binding to the copper and allows the copper to transport across the membrane. Okay, so this was published in 2011 or 12, not by us, someone else. Okay, so coarse grain simulations, imagine it's instead of atoms, you have one residue represented as a bead. So we have a bunch of beads rather than atoms. Each bead represents many atoms. Or you can have the functional group as a bead and rest as atoms, a hybrid approach. A lipid can be represented by 2 beads. So 2 beads, 3 beads, 2 for the tail. There are 2 tails, 2 beads, each bead for a tail, and the head as 1 bead. That's it. It's a very coarse grained approach. For example, like this. Charm will define a lipid molecule for every atom. This is another coarse grain where you are having different type of approximation. Martini, which is what Nisha will demonstrate, you have a different type of representation. Hook it all, very simple. 3 beats. That's it. Okay. So with that, I'll stop. My throat is aching and I have to conserve my vocal cords. So I have just a few more slides where you have this normal mode wizard which you can use in VMD and PRODY to get the normal mode data, which is what we use. And then you have the hands-on demonstration of PRODY, but she is going to show Martini, and that will be better for you, please. Do you have any questions? Okay, if you have no questions, Or if you have questions, you know how to contact me through WhatsApp or through email. Nisha, take over.
Yes, sir.
So this is Nisha. She's in her second year of PhD. Nisha, your voice is very feeble. You have to
Okay.
raise your volume. Or occupants or participants, please increase your volume. Okay. I'll just go to her room and I'll increase the microphone while she's talking. Just put a message whether she's audible or not. Okay. Continue, Nisha. You start.
Good evening, everybody. So today we'll be looking at the simple hands-on session on coarse grain simulation using Martini force field, and the MD simulation will be done via Gromax. So first, let me share my screen.
Audio. Yes. You continue. Yeah, you guys have to increase your volume. Okay.
So yeah, I hope my screen is visible. So we'll begin with the session. In coarse grain simulation, what we'll basically do is reduce the representation from all the atoms to reduce representation. Like we'll be using like 2 to 3 atoms per bead. Like that, we can change which number of resolution we want. So first, I'll show you a PDB file where all atom representation is being present. So as you can see, this is the all atom representation. So why we call all atom representation is for a reason. Every line here and every dot around you can see in the screen represents an atom, and these are the connectivity between the atom. And kindly note this, when I show you the bead representation, you can greatly see that the number of representation is getting reduced from, let's say, 4 atoms to 1 bead, like that. So in the model I'm showing today, I've represented the C alpha atom as 1 bead and all side chain as another bead. And we can change the resolution as we wish and are comfortable, and as the biological question we want to solve, and based on the structural size also. So this is the all atoms representation. So the way by which we can convert, there are a lot of ways to do it. And the one I have adapted is to use the Martinez tool. So where we can give the input file, input PDB, and we should also specify the output PDB. So here I'm generating a topology file using that to give the confirmations. And the first field I'm using here is Martini 3, and I'm choosing only the backbone representation. And here, this is the secondary structure prediction. You can also give the secondary structure sequence if you have the data with you, or else you can give this flag, and the Martinez tool will already predict the structure for you. So when you run this command, you will get the output file. I'm not running the commands. I'm just showing you the output files I have. So now we have the all atom as well as the coarse grain simulation side by side. So the one you see on the left is the all atom simulation, and on your right is the coarse grain simulation. So the difference can be clearly seen when I show you in line format. So you can see the density and the complexity of representation in the all atom simulation. Whereas in case of coarse grain, the number of representation is greatly reduced. So you can see that the central axis is prominent and the number of branches is highly reduced. So this indicates that an all-atom simulation is being converted into a coarse-grain simulation. The main idea of doing this is to reduce the computational time when using larger complexes. So with this structure, we'll move forward. So the next step involves addition of water molecule charges and all those components to the structure to ensure that. So in order to perform simulation, we should ensure that the protein structure is present in a biologically neutral condition, or in case if you want to simulate it in a condition where you have high pH or less pH, we can modify them, and the charges can also be modified. So in this can be done with the help of the component insane. Here I'm giving the modified or CG converted PDB file, and I'm giving the output file as cg.grow. This I'm using the same topology file, and here this is the periodic boundary condition. This ensures that there is no jumps between the molecules. So that it ensures when the molecules move from one side of the box, it comes around from the other side. So the number of particles within the box within which we are simulating remains the same throughout the simulation. So the shape we are choosing here is cubic box, and this is the dimensions like XYZ dimension. We can modify it as per the size of our protein structure. And then this is the concentration of salt. So normally we'll be using sodium for positive ions and chlorine for negative ions. This can also be changed in cases like for where we want specific ions like potassium or calcium. So this is in default condition. So it runs with sodium and chlorine. So solute, we are adding water. So usually that is the common solvent that is used for simulation. But in some unique cases, they will also use DMSO and other components. So based on the biological question we want to address and the other factors considering, we can modify all these components as per requirement. And finally, we are also adding the charge like for level for this protein. Based on the charge of your protein, you have to modify this accordingly. So once we do this,
Excuse me. Does Martini works with code?
Martini works with
Code?
core. What do you mean by core?
Coding, coding.
I can't get you. Can you come again?
Does Martini tool works with direct coding?
Direct coding, you're converting it into, you're meaning like script file like that? You can use that. This is a command line tool, so you can easily integrate into the scripts. It won't be a problem. You can automate the entire workflow that I'm showing you here. So once you add water molecules and ions, you can see a representation like this. So all those blue color thing that you see around it are the water molecules, and those on the center is the protein. So this clearly shows that we have to increase the box size, and the 10 dimension is not working for this. The large portion of the protein is outside the box, and we can go back and change the dimension and then run it again. So here you can see the sodium ions as well as the chlorine ions being added. So since it is so these dots round there just away from the center protein core represents the ions that we have added to neutralize the system. So with this setup, our protein is ready for simulation. The first step we have to do is make sure that our system is energy minimized. So for this, we can give all the inputs in the form of an MDP file, which is a parameter file to ensure that so MDP file is used to give all the instructions to the GROMACS to tell what cutoff scheme you want and what type of how much steps you want to simulate. So this function or this process is important to bring the system to an energy stabilized system, and then we can perform simulation so that the initial structure doesn't start from an energetically unfavorable situation, which will bias the simulation. So in order to ensure that there is no bias in the simulation, we are just energy minimizing first. So I've used 10 steps, 1000 steps here for the energy minimization. Mostly it will converge within the steps. Else you can still increase the number of steps and you can see whether this converges or not. So these are the other parameters like what are the neighboring list, how much members should it calculate in the neighbor, and the cutoff schemes and Coulomb type the charge calculations, as well as the Van der Waals interactions like non-bonded interactions. And PBC you can give it as XYZ if you are confident to have, if you're not sure what PBC you want to have, like in all domains. Else you can change it to either X or XZ, like that, the plane if you want to specify. Next, this is the grid type. We are calculating everything inside the grid. And so these are the details that can be modified not to get the output. For example, for each frame, if you want the output, you can give it as 1. Else for 50 or 60, like that, you can give 50 or 60. These are mostly concerned with the output you want from the run. So when you run this, the energy minimization, I'll show you the command to run the energy minimization step. So here, so you have to use gromp in order to generate a TPR file, which basically collects all the parameters that you have given and also combines the input data. So this gromp will take all the inputs that you have given as a grow file and the instructions that you are giving via the MDP file and prepares a TPR file which can be used for simulating the system. So here you can first in the P flag, you can mention your topology file, then the grow file, input grow file, which you generated after adding water molecule as well as ions, and you give the instruction file, and finally the output TPR file, which can be used for the simulation. And this is the reference grow file, which can be same as that of the file that you give here. So once you prepare the TPR file, you cannot read a TPR file. It is a binary file, so you cannot read that. You can only read the MDP file as well as the grow file. And then you can run the energy minimization using this command. So gmx md run minus definum. So I'm giving this definum so that all the files that this command output will be prefixed as minimization. So that is the main reason why we give here, and minus v, it will print what it's doing. It is a verbose outcome. So when you run this command, you can get all these files. So let me open the log file for you. So when you open the log file, we can see the lot of calculation that it has performed and all the input information that you have given, like how many steps you gave and all the algorithms that you have selected. And when you come towards the end, this line is of much interest to us from an energy minimization file, where you can see that F max less than 1000. This is where the energy converged. And if the energy did not converge, you have to increase the steps. So this line is very crucial in the minimization.log. If it doesn't converge, you have to change the step and you have to generate the TPR file again and then run the MD run. So if you don't update the TPR file, the changes that we make in the MDP file will not be updated. So that is important. After this step, we have to perform NVT simulation, which is under constant number of particles and constant volume. So here also we can specify the number of steps. I have kept it to the minimal extent, but the system, this process is not yet completed. So I'll show you the log file that's running now. Here I have chosen the NST log to be updated like 500 steps. So for complete 25,000 step, I'll be getting only the 5 outputs out there because I have specified 5,000 here. So I've chosen the same cutoff scheme, which is the Verlet scheme here. So usually it is always advisable to have cutoff scheme and Coulomb type as we had before. We can have the same components throughout for even for NPT. And yeah, so for this is temperature coupling. So these components all represent to temperature. So here we are simulating the system at 310 Kelvin. So we can modify this according to the condition. Sometimes we have to be simulating it at a very higher temperature in order to study like unfolding dynamics, how the bond breaks and the protein gets unfolded during the course. So for that, you have to use higher temperature. So again, based on the biological question you want to address, you have to modify the MDP file. So this is not like all standard for everybody. We have to modify the system as per our requirement. So since this is an NVT simulation, we do not have pressure coupling here. This pressure coupling is 0. We have not set it. And here I have mentioned common groups as system. So I want to simulate everything that is present in the system. There will be conditions where you'll be using protein along with a membrane. So in that conditions, you should specify which part of the component you want to perform NVT with, either membrane or protein, because for protein we'll be requiring different conditions and for membrane, some other condition will be required. So in that cases, this file will be extremely useful to specify what kind of simulation you want and how much what kind of interpretation you want to derive from the simulation. So the NVT process is not yet done. So I'll show you the log that's happening here. So for each of the step, it will be calculating all the energy angles from dihedral angles, which are proper as well as improper. Then Lennard-Jones potential, Coulomb charges, potential energy, kinetic energy, as well as total energy will be found. So you can get all this information and all these can be plotted. So since this is the NVT simulation, we won't be using these data for plotting. So this can be used to ensure that the system comes to a proper equilibrated condition, which can then be simulated. So that is the whole purpose of running NVT simulation. Even for NPT, it is only an equilibration process. And after the files are generated using NVT and NPT steps, we can run the MD production run. So mostly production run will be run for longer duration when compared with NPT and NVT. Most probably like 100 nanoseconds or 1 nanosecond, 1 nanosecond for testing and 100 nanosecond for studying. For a smaller system, easily you can run 1 microsecond also. So the main advantage of coarse-grained simulation is that you can run for very longer duration compared to that of the Alatum simulation. So you can understand the overall dynamics for a longer period of time. So that is the advantage that coarse-grained simulation gives you, but with the cost that it has a reduced resolution. So this NVT step will be generating 5 files. The first one is the CPT file, which is the time point file. So this can be used to restart the simulation from the step. Mostly for NVT step, this will not be useful. This will be useful for MD, where you cannot run continuously for like long time. You can stop it here and then resume it. After analyzing if the results are fine, you can stop it there, or you can then restart. So these are useful for that time stamp continuation. This is the XTC file. In the XTC file, the coordinates of the protein as well as water molecule or whatever the system you give will be stored. This XTC file is also a binary file. You cannot visualize it. You have to convert it into PDB file in order to visualize it with softwares. In PyMol, you can easily visualize this when you convert it into PDB. For now, I'll just load what is available and we can see what happens. So BMD lets you to see the XTC file without direct conversion, provided you are ready to give it the representation. So first you have to load your PDB file or the GROW file that you use for reference. So, yeah. So here we are not directly converted it, but we are able to visualize because of giving the PDB as the reference structure. So here also you can see the water molecule as well as the so in this situation, we can see at the bottom there are the number of frames that is being generated. So we have generated like 20 frames and you can move between frames. And you can see the frame. So you can observe that as we move, you can see that there is changes. I'm not sure whether you can observe the real-time changes because there will be lag between what we see in the screen as well as the one that is being presented. So in the similar way, we can also run the NPT simulation, which is being carried out in constant number of particles and constant pressure conditions. Next, finally, we can set up the MD simulation, and in the MD simulation, we can generate all the plots for getting detailed analysis. The basic analysis that we do are RMSD, RMSF, which are basically the deviation between the structures during the course of MD simulation. And the RMSF will give you to understand the residue level fluctuations. So in case of all atom simulation, for a residue, all the atoms will be averaged and the fluctuation will be shown. But in case of coarse-grained MD simulation, we have only two beats. And you can clearly see that in case of your PDB file also. I'll show how it is being represented in the PDB file. So if you open an all atom file, you can see for first amino acid, which is serine, we have a lot of atoms here like nitrogen, C alpha, carbon, oxygen, and C beta. Whereas in case of CG, yeah, we have just two beads. This is the main bead and this is the side chain bead. So for only one, you'll be having, for one residue, we'll be having two beads. So you can see that how much number of representation has been reduced. So this is the great reason for the reduction in the computational part. So for now, I have only the MVT simulation results. So I've just showed you. So on the same line, you can also run NPT as well as the MD simulation to understand better. So if you have any other doubts, I can help you. So would anybody have any other clarifications regarding this? Or should I repeat anywhere? Okay, so this is the data we have till now. So you can just proceed with NPT, where you'll be using pressure coupling, and in case of MD production run, we can run it for longer duration. That's it. We have to, the same procedure will be repeated. These kind of file will be generated for NPT as well as MD simulations, and we'll be analyzing the results with analyzing the data with the MD output. So these are equilibration steps. So we have, so this is the model I've generated now from PDB to course grain using Martinez 2, that is generated by unbiased CG. So sir discussed about ANMs and ENMs, no? So I'll be using SMOG to convert one of the PDB structures into the elastic network models, or you can also do it for ANM. And then the procedure of simulation is still same. You can perform energy minimization with it, and then you can go for NVT, NPT, and MD as well. So I'll show that how to perform that kind of conversion and simulation.
Your screen is not visible.
Pardon?
I think you are not sharing your screen.
Yeah, I'm just navigating to the folder and I'll then show you.
Oh, okay.
Just give me a minute. So is my screen visible now?
Yes.
Yeah, okay. So now I'll be using a tool called Smog, this like Martinez, which is used to convert into, that is an unbiased coarse-grained model. This Smog tool helps us to convert using like elastic network models. So the command here is you have to give that this is the path to the Smog, and you can give the input via -I, and -A flag represents like all atom. So you can give CA, which represents the coarse-grained representation. So I've already run all those things. I'm not just running the command, and I'm like showing you what are the output it generates. So, so you can see this is even a finer representation. So previously when I showed you the file, we had two beats. One is BB and another one is the side chain. So there are 2 beats per residue. Here we have only 1 beat per residue. So keeping in mind of the size of the protein and the question I wanted to solve, I've used only 1 beat per residue. And this gives even a finer graining, and you can simulate it for quite a long time. So as you run this command, the -I and -CA command, you'll be getting 5 files. The first one is the NDX file, which is the index file. So which will help, which will give which will help you to trace back or map the number of atoms, types like hydrogen, oxygen, and also the groups, protein, solvent, ions that can be traced with the help of NDX. And this GROW file is the structure file, just like the PDB file. You can use the GROW file for simulation. And here you get 2 contact files. One is the contact.cg. This is the coarse-grained contacts. But we'll not be using the simulation. Mostly it will be helpful for generating the models other than this model. And this is also a normal all atom contacts. So finally, it will also give you the topology file. So once this is being generated, you have to establish the new box. You have to add box and water molecules to it. Similarly, like the previous case. So just give me a minute. Actually, the visualization program is not starting up, so I'm not able to show you the grow file. So here the representation will be reduced when compared with the non-directed coarse grain models. So it is all about the question we want to solve. Here we will be running the EM step, which is the energy minimization step, and this will be generating TPR file, TRR, EDR file, log file, as well as the growth file. This EDR file stores all the data that is related to the energy. So from this, we can calculate the total energy, potential energy, as well as kinetic energy of the system. So followed by EM step, we'll be running the NVT as well as the NPT steps, followed by the MD simulation. So in case of MD simulation, here you compared to that simulation, I'm getting extra TR file than the XTC file. So this XTC file will then be converted into PDB. I'll give a one final try to show you how it looks. Yeah. So this is the finally reduced representation. I'll show you the complete representation also. So you can see the graining that has happened here. So they have the complete same sequence throughout the entire length, and the details of much of the details are being lost, and you cannot see the clear distinction between the beta sheets or loops in this case when compared with that of an all atom MD. So this is the key difference between them, and as it reduces the time, it also contributes to the reduced understanding or some of the biological data which might be influenced by the which might be influenced by the side chains, might be lost, and that kind of information cannot be inferred from this. And if you try to infer, that will lead to a wrong conclusion. So it is very important you understand the problem you are solving and then choose which kind of representation you want and the level of coarse graining you want. I'll run the simulation and you can see it like it gradually changes over time. So this is being run for like 100 nanoseconds. In coarse grain, we can't actually say it is nanosecond. We should refer it as in the time frame, time steps. So this happened for like, I'll show you the time steps when it gets completed. And I'll also show the MDP files I've used for this simulation. So when you complete this simulation, you will get the system along with the water molecules and other ions, which you can remove that and then perform the analysis. Because we are using the water molecule and the ion just to ensure that the system is in equilibrium and biologically favorable condition. So it is okay to remove them and then perform the further analysis with only the protein components. Unless and until that ion is an integral component of your protein or it is important for the biological function we are dealing with. So So for this system, I've calculated the projection as well as the covariance matrix. I'll show the projection that I've got in like for first two principal components. So this kind of plots will help us to understand how many conformations that this protein preliminarily explores. So this gives a very vague understanding of like it has like two major minima like that. So which has to be further extended by using the free energy landscape plots. So that will give you even in-depth understanding of how many conformation that these protein adopts, and is there any significance between these, how do they change, all those things we can understand with further analysis. So for now, this is what I've done. I've just given the projection plot for first two principal components. And when you increase the number of principal component representation here, you can see that there's a change, and sometimes you can get the confirmation. So based on as much as information you give, the confirmations or the minima to be more concise. So the number of minima representation will be demonstrated here. So again, here also we should be very careful on using how much representation or how much components that we should be using. So this can can be studied by using trial and error method and performing a lot of modification with the current simulation. Okay, so I'll also show you the free energy landscape for this routine. So this has been plotted with that, the second plot I showed you using the principal component analysis where I've used the first three components. So you can see that there are three like prominent minimas here, and of those comparatively, this has like greater minima. So this can be used to understand how much conformations they adopt and which conformation is more favorable. Further, then you can extract that which conformation is present in this minima. So that information can also be derived after generating this plot, and we can visualize and compare between the two structures that is present, that is dominant in this protein. So these can be used to analyze. So when we run the coarse grained simulation, so these kind of information can be easily analyzed because of reduced size of the trajectory and other computational power also. But in case of all atom simulation, these calculations will be extremely time consuming as well as computationally expensive. So that is the main ideology where we come to the coarse grain simulation. So this is about the smog tool, and only the model generation will be difference between the non-biased coarse grain model and that of the smog generated models. Other than that, performing the energy minimization, like adding water molecules, ions, and performing energy minimization, all those things will be similar for both the models. So only the conversion of all atom simulation to the coarse grain simulation requires different tools or different conditions. Other than that, you can simulate most probably both of them in a similar condition using the same engine. So here in our lab, we use the engine GROMAX, and there are also some other engines which can be used like NAMD and other tools which can be used for simulation and drawing up meaningful conclusion from this results. So this is about the smog tool. So do anybody have any other doubts regarding smog? I'll show you the MDB file. So this is the MDB file. Here you don't see Martinez on the top. In the other file, you can see the Martinez on the top because it is made made to match the parameters or the system that is being generated by with the help of Martinez. But here this is completely generated with smog, so it can actually use directly the MDB file which is used for GROMAX. So this is the time steps and the total number of time steps that I was talking about. So here it is like 1 crore steps in order to get the simulation that I've shown you. And I've written the files out for every 1 lakh steps. So even when visualizing, if you don't want to visualize the entire trajectory, we can skip some of the files using skip command when you convert the XTC file into PDB, only for visualization purpose. But when you want to analyze the entire trajectory, you should use the entire trajectory so you can get complete information about the system. And you can also plot the RMST, RMSF plots for this, which helps us to study how the system changes during overall process. And the energy plot should be in equilibrated condition, and you do not see any major fluctuations. So when you see a major fluctuation in the energy plot, it says that the system is undergoing a major change or a conformational movement, and it is of significance. So that has to be taken care. So here most of the conditions that we used, except the Coulomb type, we have used cutoff here. And yeah, most probably most of the components are like similar for both the coarse grained as well as the elastic model that is being generated with the help of smog. So second is the NVD. So all these commands can be automated with the help of scripts and you can run all these things. But the only thing is during the preparation, it is always advisable to do it manually so that you can visualize it at each step and ensure that the protein is properly prepared and you do not waste the computational time. So I would say that during the preparation, like for example, removing of ions, water molecules before the processing and addition of water molecules and all the components after the conversion, that is all-atom conversion, all-atom to coarse grain conversion, we can use all those components you can do it manually. So to ensure that all the steps are taken care of and there are no errors getting in, and sometimes you have to tune the steps also. For example, for some protein you should add greater charges, for some other protein you should add lesser number of charges. So in order to understand and look at for this, even let's take the example that I showed you before. I had a protein where the loop is like out of the box. So in those conditions, if I visualize it before simulation, I can change the box size and I can make the water molecule fill the entire box. So if else the simulation will run and at the end of it, I'll notice that and that will be a computation. So it is always suggested to manually visualize all the preparation step. And then from the energy minimization, after you ensure that it is energetically favorable or it is minimized, you can run the NVT step, NVT as well as the MD simulations. So that process can be automated over all the files for all the protein for like 100 or 20, 200 protein simultaneously. So this is about smog and the coarse grain simulations. So if you have any other doubts,